Okay, I make that 4 o'clock. So, good afternoon, and welcome to day number. Oh God, what day number is it? It's Wednesday, so day 8. Oh. Okay, today's going faster than last week, which I guess is a good thing. Okay, so day 8 of our bioinformatics tutorials. So today I'm going to carry on talking about Grep. So I introduced you to Grep yesterday afternoon, and Grep is a tool, and I can never remember what Grep stands for, but Grep is a tool which allows you to search for patterns in a file. So it allows you to take a text file with indeterminate contents and search in that file for occurrences of a particular pattern of text. Now that pattern of text can be defined as just as a standard string, so just a phrase effectively that you want to find in your file. But you could also define that pattern as an actual pattern, as what's called a regular expression. So something which contains variable elements, which means that it might match many different things. So we looked yesterday at some examples of using Grep, and we were working mostly with our piece of data that we were looking at earlier in the week, so a table of differentially expressed genes that we were looking at earlier in the week, and using Grep to pull particular genes out of that file by matching gene names and ensemble gene IDs. So just to refresh, I'm going to grab my virtual machine. Here we are, which is up and running. And I'm going to change my directory into share week 2. And in there, if you recall, I have my CSV file that we downloaded on Monday. And we've also got a couple of files that we've generated as a result of processing that file with cut and with sort, which we did on Monday. So cut gives us, so if we look at the first few lines of our example TSV, we've got 8 columns in that data, if you recall. We used cut to get just the first column and the last column, and that's what I've got in ID symbol.csv. That's the first column and the last column, which is the ensemble gene ID and the HGNC gene symbol for that particular gene. And I also used sort to reorder the file, and that's what I've got in sorted CSV. That is that file sorted by the adjusted p-value, which is the 7th column in this file. And if you remember, what I did before I did that sorting was I took the header line off and I just sorted the data and appended it to a file into which I just put the header line to make sure that the header didn't get sorted in amongst all of the data. So that was achieved by doing that and by using sort, which was a useful thing to be able to do. Then yesterday we were looking at using Grep to pull out particular lines from this file. So in this case, I decided that I would use a regular expression. So I'm using capital P, to tell Grep that I want to use a regular expression. And I was looking for the septin gene family. So I wanted genes which matched sept, S-E-P-T, all in capitals, with 1 or more digits afterwards. And the other thing I wanted to make sure is that occurred at the very end of the line, and that was because we had some genes which weren't actually members of the septin gene family, but were kind of related genes, like an antisense gene and things like that. And their numbers, they had things after the numbers, so like a dash and an AS for the antisense. And so in order to retrieve just the septin gene family, we've stuck a $ on the end, because that's saying ensure that this match occurs at the end of the line that we're pulling out. And that, from example.csv, extracted the results from our gene expression experiment for the septin gene family. So that's the 1, 2, 3, 4, 5, 6, 7, 8. Actually, let's count them. -C, put a -C into the command, and that counts the results. 12. The 12 members of the septin gene family that you find in these particular gene expression results. Just to clarify, just to make sure that we're absolutely certain, if we don't include the $ at the end, then we get a few extra results. So sept14p19 here, sept7as1 here. So a few extra results that aren't actually directly members of the septin gene family. I just want to test something out, because there's another option of grep which I always forget and which I think might be useful here, and that is -w. -w is telling grep to restrict matches that are a whole word. So it requires that this match forms a word on its own in the file, and I think that will effectively give us the new line restriction at the end of the match, because a new line can be a word boundary. A comma can also be a word boundary. So this means that if the gene name wasn't the last entry in the file, then if it wasn't the last entry on each line, so if it was in the middle somewhere, then using -w to say we want this to be a whole word means that it will treat the comma as a word boundary, and so it would still work even if the gene name wasn't the last thing on the line before the new line. So I just want to check that that works, and indeed it does. So that finds our 12 septin genes and none of the extra ones that aren't actually members of the septin gene family. So that's another useful option for grep. Actually, it has picked up the antisense gene, hasn't it? So the hyphen must be a word boundary as well. The hyphen must be a character which grep considers ends a word. So actually, maybe that isn't the best way of doing it in the world. Okay, so that's the -w option. So it hasn't quite worked the way that I'd hoped, but nevertheless can be quite useful in certain circumstances. Okay, so that was yesterday, and what I wanted to do today was to continue to talk about grep for a little while, because as I think I alluded to yesterday, and as I think some of these examples demonstrate, grep is both extremely useful and extremely complicated. And as you can tell, it quite often takes quite a lot of kind of experimenting and testing to get the command that you want for grep exactly right. And I just wanted to show some slightly more complicated examples which might kind of illustrate the uses of grep a little bit more and may come in handy later on. Okay, so I'm just going to summarize some things about grep then for you, and that brings me to Jacob's picture of the day. Yes, I can tell you what this is because it's not immediately clear. So this is a picture of puppet made from a wooden spoon that Jacob made at Christmas, which is a reindeer. So this is a wooden spoon reindeer rendered on a Microsoft Surface. So that's what the picture today is. It's not what might immediately spring to mind when you look at this. I'm not sure what does immediately spring to mind. I guess it depends on the way your brain works. Right, okay. Let's remove the picture of the day today. It's going to catch up, so let's hit refresh on the whiteboard. Ooh, every day you get to see this, what fun. Okay, so that's refreshing, and I'm going to write some things about grep while it's refreshing. So grep pattern file. Okay, so there we go. That's the general mode of operation for grep. Okay, so grep pattern file. And then we've got some useful options for grep as well. And I just want to grab a reference document for this. Bear with me, my screen's gonna jump around a little bit. Don't mind me. There we go. Right. Okay. Sorry, back to where we were. Okay, so some useful options for grep. So obviously with this is our general way of using grep, and you would normally have your options in here. And options by their very nature are optional. Things that are optional, you'll see this in man pages, and so on. Things that are optional are often written in square brackets to denote the fact that they're optional. So I'm kind of using the syntax here from man pages. So some useful options for grep. We've covered some of these already, and some of these we won't have covered. So it can be, I'll introduce some new ideas here as well. So options -C, we've already covered, counts the number of matching lines. -I we talked about yesterday, to make the search case insensitive. One we haven't covered yet, -O, that's a lowercase o. We'll come to this later on. But this means that rather than giving you back the whole line, grep will just return, the O stands for only the matching portion of the line. So instead of giving you back the whole line, it will give you back only the bit of the line which matches your pattern. Okay, which can be quite useful if you want to extract data from a file in a particular way. -W we've just covered. So -W is will only give you lines containing matches that form whole words, and what we need to know in order to figure out whether this works for our use case or not is what constitutes the boundary of a word, what constitutes the beginning and end of a word according to grep. And I'm guessing, but I think the man page will probably tell us. So let's see if it does. Let's type man grep, and then man returns your the text of the manual in a pager application, and less, which is usually the pager application that's used, allows you to search in the text that it's displaying by typing a /, and then some text that you want to search for. So I want to search for -W to see if we can find the argument, the matching word argument, and see if it tells us what the word boundary characters are. Here we are. Select only those lines containing matches that form whole words. The test is that the matching substring must either be at the beginning of the line or preceded by a non-word constituent character. Similarly, it must be at the end of the line, followed by a non-word, or followed by a non-word constituent character. Word constituent characters are letters, digits, and the underscore. Okay, so that's it. So anything other than letters, digits, and underscore are non-word characters, and they can form the boundaries of words. So that's why that's not a full word. That doesn't match a full word. So those were excluded. But the sept7-as1, that wasn't excluded because the hyphen forms a word boundary, so it was matching the sept7 bit and not the dash antisense dash as1. So that was not being excluded by our word boundary criteria. So that does explain that, and this is where man pages can really help you kind of elucidate the finer points of the functioning of a particular command. Okay, so that's -w. That's a useful option for grep. Another useful option, which and there's another one which we haven't talked about yet, is -v. And -v is, in lots of commands, means verbose. It means run this command and give me lots of information about what you're doing. So things like cp, when you run cp and you copy a file and it doesn't tell you that it's done anything or what it's done or anything like that. If you run cp with -v, it means verbose mode, and it will tell you what it's copying when it's copying, which can sometimes be quite useful, especially if you're copying very large files. But in grep, that's not what -v means. -v in grep means select non-matching lines. So it's like an inverted grep. So instead of only returning you the lines that match, it returns you lines that don't match. And that can, again, be extremely useful under certain circumstances. Okay, so that's another useful option for grep. We've seen --color, which on most systems is the default, but isn't on macOS, for instance, but now on most systems is the default. And then the final thing is -p to turn on our regular expression engine, which again is something that works on Ubuntu, so it will work in your VMs, in your version of Ubuntu that you've installed. But this doesn't work on, for instance, macOS, where the version of grep that is distributed with macOS is different to the version of grep that is distributed with Linux, and that's because macOS is built on an operating system called FreeBSD, which is similar to Linux, to the kind of basis of Linux operating systems, but is subtly different and uses older versions of some of these core utilities. So the version of grep that you've got on OS X by default, on macOS by default, doesn't enable you to turn on Perl regular expressions. You can use a package manager like Brew on macOS to install the GNU, what's called the GNU version of grep, and that's a version which will have all of these features. So if you wanted to do that, if you wanted to explore Brew for installing tools like that, then that can be quite a useful idea. Brew will also give you access to wget, which is another tool that by default you don't have on macOS. Okay, so moving on, I'm going to talk a little bit more about regular expressions, and particularly about those character classes which we looked at yesterday. So yesterday, I'm just going to shift this over to the left. I've not got much space on the right. That's okay, fine. Okay, so I'm going to take this up here. So yesterday we looked at this single character class \d, which matches a digit character. That's not the only character class that we have available to us in these regular expressions. So there's the inverse, which is \D. That matches, instead of matching a digit, that matches a non-digit character, so any character that isn't a number. You have \T, that's a tab character. You have \n, that's a new line. So you can do that as an alternative to the $sign at the end of your match. It's effectively the same thing. You have \w, that means a word character. So that's like the -w option for grep. That's going to match any alphanumeric. It's going to match a dot. It's going to match the underscore, but it's not going to match a comma or a space or any of those things. You've got the inverse of that as well. So capital W, quite difficult to tell them apart in writing, but that's a non-word character. So that's anything that doesn't qualify as a word character. And then you've also got white space. So \s is any white space character. So that will be spaces, tabs, new lines. They're all white space. And the inverse of that as well, \S is non-white space. So these are all different character classes that you can use in your regular expression for matching. You can also use dot. That means any character at all. Anything at all will match a dot, and you can expand all of these by using either plus or star, where plus means one or more matches and star means 0 or more matches, which can be helpful. It sounds like it wouldn't be helpful, but that can be helpful in certain circumstances. Okay, so that's not an exhaustive list, but is a lot of the character classes that you can use to define your regular expressions. And these things can be quite useful to build up patterns which generally match a selection of things in your file, rather than matching very specific things, so having something which only matches one occurrence of one thing in your file, which can be useful, but regular expressions can be much more powerful. And what I'm going to do is I'm going to dive into the UniProt entry that we downloaded last week, to show you some examples of grep in action, so that you can get an idea of the kind of things that you can do using grep, and then using regular expressions to try and expand the power of grep a little bit. So we're going to go to back to our virtual machine. So hopefully that obviously that's a bit of an information dump, and there's a lot of information there, but I'm going to try and show you some of this stuff in action now. So we're going to go back to our virtual machine, and we're going to work with the UniProt entry that we downloaded last week, which is squirreled away in our week 1 directory. So we're going to cd one level up and then back down into week 1 rather than week 2, which is my present working directory. So we'll ship over to week 1 and ls to remind us what's in there, and we're going to have a look at this the text file, so q9 byf1.txt, and we're going to have a look in there for some particular things. So there's 2 things I want to look for. The first thing is I want to know the species that this UniProt entry came from. Now I know that we downloaded it and we went to UniProt and we downloaded it, and we know that we got the ACE2 receptor from human, so we know what the answer is going to be, but we're demonstrating a tool here. Okay, so we're going to use grep to find the tax ID, the taxonomy ID in this file, and the nice thing about this is we can write this so that it will find it in this file, but we can also write it so that it will find it in any UniProt entry that we care to download. So the first thing that I'm going to do is I'm going to use grep to try and track down the line which has the taxonomy ID on it. So I'm going to do this without really knowing what that line of the file looks like. Okay, so I don't know if it says if it's talking about taxonomy with the full line. I don't know if it's using an abbreviation. So the first thing that we're going to do is we're just going to grep, and I'm going to do it in a case insensitive way. So I'm going to do it as broadly as possible, and I'm just going to search for tax, because I don't know if this is going to be abbreviated in the file or anything. And if I start searching just for the full word taxonomy, then it might not find what I'm looking for. So I'm going to grep with a case insensitive, so that it doesn't matter what the capitalization is like. I'm going to search for tax. And I'm going to do that in this q9byf1.txt file. Okay, so that's my first grep to try and track down this entry, and actually that's worked straight away to give me the thing that I wanted. Right, so in this case, in this file, the three letters TAX only occur together on one line in the file, and that is the line which contains the NCBI taxonomy ID, which 9606 is the tax ID for Homo sapiens. So that's telling us that this comes from a human. But if I wanted to generalize this, I can't rely on the fact that the three letters TAX are always only going to crop up on that line. So I want a general pattern that is going to match that line in this file, but in any other file that I download from Uniprot, and is going to match only that line. It's not going to be so general that it might match other things in the file. How am I going to do that? So I'm going to define as much information about that line as possible, and see if we can retain this match. Okay, so grep. This time I'm going to look for lines which begin with OX, and see if this is the only line that begins with OX, because it may be that OX is effectively the taxonomy line, and that might be sufficient. It is, but I can't guarantee it. So, okay, let's see. Is that a space or is that a tab? What do we think? What is the bet? I think I'm not sure. So I'm going to turn on Perl regular expressions, and I'm going to try putting a tab character in, and then NCBI. Okay, so this time I'm expanding the match a little bit to make it more specific. And it's all these things are only ever going to match one line or no lines, because this is the only line that we're matching. But we want to make this as specific as possible, so that if we do repeat this search in another file which might have more OX lines, then we're not going to suddenly start identifying multiple lines in the file. So that tells me that that between the OX and the NCBI is not a tab character, okay, because it's now failed to match that particular line, that one line that we're interested in. So that's not a tab character. So it might be multiple spaces. So in that case, instead of looking for a tab, we're going to look for one or more space characters. So space with a plus says at least one space, but there's no limit on the number of spaces. So where \s is a white space character from our list of character classes that I wrote out here. Okay, so \s plus says match one or more white space characters between the OX and the NCBI. And we've got our match back again. And this time we've expanded our match so that it's a little bit more specific. Okay, so we'll just finish this off by making it as specific as we can. And so I'm going to finish putting tax ID and then equals. But if we want this to match in any file, that may not the file that you've downloaded may not be for a protein from a human. So your tax ID may not be 9606. also tax IDs range from, I think, from a single digit up to 5 or 6 or even more digits. So we can't guarantee also that it's going to be 4 digits. So again, tax IDs are numbers, so we want it to match digits, and we want it to match 1 or more digits, because our tax ID might be 1 digit, or it might be 6 digits, or it might, in this case, it's 4. And this will match, apart from the semicolon at the end, which we could add in, but apart from that semicolon for now, this will match all of that line. And that's quite, that's a nice general pattern. And we could now use that pattern to search for the taxonomy ID in any UniProt file that we downloaded, which is a relatively benign thing to be able to do, but it's quite useful. The other thing that you might want to do is to actually extract the identifier itself. So having the line is interesting and can be quite useful, but actually the thing you might want is the taxonomy ID itself to take into some other, so maybe you want to find out what organism that taxonomy ID represents. So maybe you don't know that 9606 is Homo sapiens, and maybe you want to extract the taxonomy ID and use it to do a search in the NCBI's databases, which there are command line tools for searching the NCBI databases. So you could extract the tax ID and use those command line tools for searching the NCBI databases for what that organism actually is, in which case you want to be able to actually extract the numbers from the file. So we can do that, and we can do it with the best way to do it is to find this matching line and then extract those numbers using a second grep. And you do that using output redirection. So we've got this grep which matches the line. So this returns just a single line, which gives us the NCBI tax ID. But maybe we want just the number, and to do that we can redirect that single line, so the one line that results from that particular grep, and we can use a second grep to extract just the number. Okay, so in this case we're going to do a second grep. We're going to use Perl regular expressions again, so we're going to use one of our generic character classes rather than a specific string or a specific pattern. And this time we want to use another option which we've not actually really looked at yet. That's the -O option, which I mentioned over here. So -O gives you back only the portion of your line which matches your pattern. Okay, so only the matching portion. So -O is our second option, which we're going to pass here. And this time we just want the numbers. So that's our pattern for that is \d for digit, and we want 1 or more digits. So \d plus gives us back 1 or more digits. And this will return, instead of the whole line, that's what the first bit gets, but then the whole line is processed further by a second grep to return us only the 4 digits that match our second pattern. And that gives us back our taxonomy ID, which then we can reuse in other ways. It can quite often be the case that you'll want to do these kind of greps to pull little bits of data out of your file and use that little bit of data in some other process. So you might take that taxonomy ID off and use it somewhere else. And so the second example that I wanted to show you was a similar thing, but to pull some data out of the reference lines in this UniProt entry. So UniProt entries are backed up by published data, generally speaking. If your protein is in UniProt, that's because we know the protein exists, so somebody's published something about that protein somewhere. The information about the references that back up a UniProt entry are stored in the lines of the UniProt file, which again have a particular 2-letter code at the beginning. So whereas the taxonomy ID was in this OX line, the references that underpin a UniProt entry are found in the RX lines. So we can grep for RX at the beginning of a line, and that will give us the reference lines for this particular protein. So in this case, there's quite a few of them. And again, we might want to go and chase up these. These PubMed entries to see what the papers are that have been written about ACE2, because they may be interesting to us. In which case, we can extract the PubMed IDs from these lines. And as you can see, there's quite a few here. There's quite a number of publications about ACE2, which I guess is not altogether surprising. So we can build a similar regular expression to the previous one, and use a pipe in a similar way to the previous example to extract the PubMed IDs from these lines. We could even use those PubMed IDs to construct URLs to give us things that we can click on to go and get these papers quite quickly. And we can maybe explore how to do that another day. But right now, I'm just going to focus on using grep for extracting this information. Okay, so we're going to build this up in the same way as we did the last one. So we want to pull out these lines first of all. We can do it with just RX, but we want to make sure that there's a PubMed ID on that line. So it might be that some of the publications aren't necessarily indexed by PubMed, so we don't want those. So we only want the PubMed ones. So we're going to build this up like we did before. I'm adding in a character class here, so I'm going to put in the space symbol like I did before. So I want to match multiple spaces between RX and PubMed. And so in that case, I want to turn on Perl regular expressions so that character class is understood. If I don't do that, okay, so if I do this with Perl regular expressions switched on, then it still matches my RX lines. If I turn Perl regular expressions off, grep doesn't understand the \s anymore. It doesn't interpret it in the way that you want it to interpret it, and so it doesn't find those lines anymore because it's looking specifically for the characters \s and plus. It's not looking for white space anymore like it is when Perl regular expressions are switched on. Okay, so we'll switch the regular expressions on, and then we want PubMed equals. So that gets us that bit, and then we'll have the digits as well, just to make sure that we're really getting what it is that we want. So again, although all of these PubMed entries have identifiers the same length, again, that's not a guarantee. So rather than restricting it to a specific number of digits, I'm going to use plus here to get any number of digits as long as there's at least one digit. And that's just making sure that we are definitely getting the lines that we want that have PubMed identifiers on them. Okay, so that's the other thing I should say, actually. Technically, those PubMed identifiers may not be the first thing after the RX, so this may not always work. It so happens in this case, it is always the case that it's the first identifier that follows the RX at the start of the line, but you could probably achieve similar goals by just searching for the PubMed string on its own. I see a question about the equivalent to -p on a Mac. As I mentioned before, you can install GNU grep using a piece of software called Brew, BREW, and that will allow you to install a different version of grep that has -p. Alternatively, there are ways of defining character classes in grep itself that that are more complicated than Perl. So the reason that I use Perl regular expressions is they're relatively simple. The character classes are, you know, backslash and a letter, generally speaking. In Grep itself, I think the way of defining a digit, if we search for digit, so it's these character classes are written like this, with square brackets. So you can do, instead of doing \d, you can do open square bracket colon digit colon close square bracket, 2 colon, sorry, 2 square brackets, like that. How you do multiple ones, it may still be a plus. Let's have a test. I'm not sure. No, it's clearly not a plus. So how you do multiple digits, I'm not entirely sure of. There you go. So you have to escape the plus. So you have to do \+ to say I don't want a plus character. I want a meta character called plus, which is saying, so I don't want this to be interpreted as the plus character. I want it to be interpreted as I want more than one plus. Sorry, more than one digit. So this is the Grep way of doing character classes, and this is why I prefer the Perl way, because the Perl way is just \d+, which is in theory much more straightforward, although it does kind of predicate that you understand Perl regular expressions, which I realise is not necessarily going to be the case for everyone. So there you go. That's our lines which contain our PubMed IDs. Now we want just the PubMed bit of that. So first thing that I'm going to do is, these lines are slightly more complicated than the lines that we had for our taxonomy IDs, and as well as containing PubMed IDs, they also contain DOIs, and I don't want the DOIs to confuse things because they have multiple digits in a row as well as the PubMed IDs. So in order to do my pipe here, I'm not going to pipe the whole line into my second grep. So I'm going to restrict this first grep to only the matching bits of only the bits of the line that match my pattern in the first instance. So -o to restrict my match to only the bits of the line which match my pattern. So that gives me back PubMed equals number. And then to get the number, I need to do a second grep with just those results. So I pass the output of my first grep into a second grep, again with Perl regular expressions, only the matching bit, and this time I just want the multiple digits. I don't want the PubMed equals bit. And this will give me a list of PubMed IDs, which are a list of PubMed IDs which are about or contain information about ACE2, which again can be a useful thing to do. And because I don't know how to do it off the top of my head, I'm not going to do it live, but I will figure out, and maybe you could also try and figure out, although I'm not sure I've necessarily given you all the tools to do it, but we could try and figure out how to turn that list of identifiers into a list of URLs. But I'm not sure that I've necessarily given you the tools yet for doing that. So I will try and figure that out between now and tomorrow afternoon, and I'll give you that solution tomorrow. But if anybody feels really brave and feels like they can try and figure it out, there are probably ways and means of doing it using only the tools that we've introduced so far. but I don't think that's necessarily a given. So I don't want to sell you false hope, but I'll figure it out overnight, and I'll show you a way of turning those into URLs. Our terminal emulator on Ubuntu should make URLs clickable automatically, so we should be able to go straight from URLs to clicking through to PubMed to actually get to the papers, and I'll try and figure that out. As I said, I'll try and figure that out overnight. Okay, so that's everything I wanted to talk about today. I've spent 2 hours, best part of 2 hours, on Grep because I think it's a very important tool, and I think it's something that we will be coming back and using more as the days and weeks go by. Tomorrow, so obviously I've got 2 days left this week. Tomorrow, I think I'm going to begin to introduce scripting, and actually part of the answer to how to turn these into URLs may well be to write a little script. So it may be useful to use that as an introduction to scripting. So I'm going to start to talk about scripting tomorrow, and how to turn our single commands that we've typed interactively so far into little programs. So we're going to start to write programs which we can begin to do, instead of just doing one thing in a single command, or maybe a chain of a few little things, we can start to do more complicated things in a more automated way by writing and executing programs. So I will begin to talk about scripting tomorrow. Again, that's something which may take more than a single lesson, so it may be that will spread itself over a couple of lessons. So that might fill the rest of this week. Okay, so that will be tomorrow, and so on. Feel free to join me when we start to talk about scripting then. I hope everyone's keeping up. As usual, any questions in the comments as we go, or find me on Twitter. I've had quite a few DMs on Twitter from people asking questions. I'm perfectly happy to try and find the time in amongst my other work to address those questions, and come back tomorrow, and stay well, keep safe, and I'll see you all on the 2nd of April. And we've managed to put April Fool's Day behind us without anybody being completely ridiculous on the internet today, which is quite good, I think. I've not seen anything at all that made me really cross this morning, so that's nice. So see you all tomorrow, and au revoir, bye-bye.